A simple toy called jumping bean can be constructed by putting a metal ball inside a pill capsule placed in an inclined surface. At a certain inclination, the jumping bean will tumble down in a rather surprising way, simply standing up and upright, flipping end to end instead of rolling. Investigate its motions and find the dimension of the fastest and slowest beans. So I would like to point out that the part in blue is telling us how to assemble our toy. The other part is telling what are we interested in, what part of the movement we are interested in. Rather than just rolling or sliding down, we are interested in tumbling. So we are going to focus on that because that's the main focus of the problem. So, what do we need to extract from that? We need to investigate its motion, which is the part in green, and find the dimensions of the fastest and slowest beans for a given inclination. Okay, so I will divide the presentation in the following way. I will have phenomenon observation with the experimental setup and how we measure uncertainty estimation. How we measure uncertainty, then our theoretical model with equations of motion, computational implementation, condition for tumbling regime, and optimization. Optimization just meaning finding the slowest and fastest bean. And experimental analysis with the theory experiment comparison for different beans, the tests we make, of course, the experiments we make, and then checking predictions. The conclusions and further insights, I will present the final results, consider some model limitations, and the final considerations. Okay, so first phenomenon observation. So we used a high-speed camera, the Sony A6300 mirrorless camera, tripod, inclinable plane, 5 different sizes of bearing balls, and 5 different sizes of pills, matching the sizes of the bearing balls in terms of the radius. The radius of the ball matches the radius of the cylinder, of the cylindrical part of the pill. So the experimental setup, we have a parallel recording, so we avoid parallaxes in our experiment. That is, if it's moving in some other direction that is not captured by the camera, we might underestimate its velocity or location, or displacement. Then repeating the experiment several times under the same conditions, give type A uncertainty according to the guide to expression of uncertainty in measurement. 2018 we used. It's a statistical type of uncertainty that is given by the standard deviation. So, and a high-speed camera, of course, to track the position of the beans. So first, the experimental setup, we repeated many times with the different beans. Here is just an image. We use for data acquisition tracker. It provides a very accurate a very accurate and precise measurement of position, but it does not provide a good uncertainty estimation. That's why we chose to use the statistical type of uncertainty. And this setup favors the repeatability of the experiment because we just start at the same point. We release the pill with the same initial conditions, and then we can easily use our type A uncertainty. All right, so theoretical model now, which is particularly the most interesting part, I believe. So first, a qualitative explanation. Whenever of course, the part when it rolls from the top end to the other end, which is the second image there, it's quite simple. It's just a ball rolling down. But when it reaches the other end, then there is of course, these two are F, but it's qualitative, so there are different Fs. So there is a torque there, and the ball is attached to the ending edge of the pill, and this torque is stronger because usually stronger, not always, but usually stronger because the pill is too light, and then the bean just flips. Okay, now mathematical model, degrees of freedom. So at first, we can identify the generalized coordinates, theta B, theta C, and y, being theta C the rotation, theta B the rotation of the angle of the ball, theta C the rotation of the capsule is the theta in the image, and y is the position along the plan. And you can see that we defined it inclined already because it's useful for us. And finally, there are 3 degrees of freedom. However, we can say that there are only static friction forces, meaning that the ball is always attached to an end and the capsule is always attached to the plan. So those are 2 holonomic constraints, and this, of course, reduces our degrees of freedom to 1 because of the equations right there. It's written exactly in the form of holonomic constraints, so that we see that these that we can reduce the number of degrees of freedom. Of course, we are not considering sliding friction. We considered it, but it's not useful, and we can discuss that during the fight. I will not have time to go into such a complicated model right now. So, but this approach is even better. We can discuss that. So here are the schematics of how we're gonna write our equations, and we have the different variables there, and we write the Lagrangian of the system for, of course, for the tumbling part, and then for the rolling down part is even simpler, and it's a high school kind of problem. Of course, here we are using Lagrangian, which is not a high school thing, but I just thought about being consistent with using, instead of Newtonian physics, using an approach based on the least action. So then we use all the Lagrange equations to find the equations of motion for the tumbling part and the rolling part. And finally, of course, if you look at these equations are quite nonlinear because we have a cosine of theta there. And yeah, that's cosine of theta makes nonlinear. The other one has a constant acceleration, so it's just integrable easily because it's just the rolling part. So notice I used y and theta, even though they are practically the same by the holonomic constraints. But it's useful to use theta and y instead of just theta or just y. You're gonna see next, because one we have to integrate for a length displacement and the other one for angle displacement. Okay, so the first part, we say the ball roll down from the top from the top edge to the end edge. Okay, so we use a MATLAB code that this one is pretty easy. We keep track of position as a function of time just by integrating this directly 2 times. Then when it hits the other end, we conserve angular momentum and we transform linear momentum in angular momentum by the formula, by the equation given. And that gives us a new initial rotational velocity. Then next, we have the equation of motion, and giving the initial conditions, we of course take the theta initially to be 0, and then we just integrate it until it's 2 pi. And because this is not, we cannot, I think I made a remark here. So because we cannot specify the time interval under which we should integrate the equation, we run the program, the simulation, several times so that the final output is close enough to 180 degrees turn of the peel, and then we find how long it takes. And therefore, by knowing the relation between theta and y, we know the position as a function of time. So it gives an integration like this. This is a condition for torque, because I'm short on time, I'm gonna skip this. We can discuss it on time. It's just how strong the torque must be so that it rotates, it tumbles. So we have this theoretical prediction for mass ratio, radius, and the length L, the characteristic length L we defined. And then this shows us the average velocity for the length ratio and the mass ratio, which is what we're needing. Experimental analysis, we have these beams we use. Here are the results of the integrating and finding position as a function of time, and these are quite good results for tracking the beam. And here is predicted fall time, how long it takes to go through given plan. And final the insights. So we made a prediction about how fast it's going to be, so we can choose the fastest and the slowest beam based on the graphs and based on our restriction we showed in that conditions for tumbling part. And so the phenomenon was properly answered. So the limitations of the model and the final considerations is sliding friction was not considered, but it's not as important because it will give, or it will give absurd predictions, or it will not give us anything, or it will give the same results as this regime of this model. This formulation provides actually meaning results and predictions, and it works greatly for the tumbling regime, which is the one we interested. These are our references. Thank you.
The problem statement again. A simple toy called a jumping bean can be constructed by putting a metal ball inside of a pill capsule. Placed on an inclined surface at a certain inclination, the jumping bean will tumble down in a rather surprising way, seemingly standing upright, flipping end to end instead of rolling. Investigate its motion. Find the dimensions of the fastest and slowest beans for a given inclination. Here I have highlighted again what I think are the main parameters and main questions to consider, namely the dimensions of the fastest and slowest beans for a given inclination. In general, the approach would then have experimental tests. I would expect some sort of theoretical concept because this is a very good mechanical problem that you can solve. And then I would expect some sort of a comparison between the two. To summarize the report first, they gave a qualitative explanation and which they said was using cameras and talked about how the bean is actually going down, what happens, and we see very clearly the problem. And this was the experimental part that they began with, and they talked about using a high-speed camera and getting the results and using Tracker. And Tracker is a very good software for this thing, so I really appreciate that you use that. And especially that you use the statistical uncertainties and reproduce it a lot of times to get rid of these uncertainties, or rather to make them smaller, not to get rid of them. I also like that you had the MATLAB computation, which they did, and I think that it was a bit unclear, but they used 5 different balls and I think 5 different capsules. For the theoretical part which came, then they had a qualitative explanation of the phenomena, okay, with the free body diagrams and stuff like that. Then they said that, okay, we have 3 degrees of freedom. If we consider the rotation of, let's say, the ball, and then we consider the rotation of the capsule. However, they said that they didn't consider any friction, and I wasn't completely sure of why this was the case. I think they might have gone a bit too fast to, or rather a bit too slow to actually reach the point where this could be considered, but we can talk about that in discussion. I like that you considered a Lagrangian and then went to the Euler-Lagrange equations and actually got got some results, and which you, I think, said ended up not being 3 different degrees of freedom, but rather just 1, using the holonomic constraints, which came due to the fact that actually no friction was considered. So in theory, your y would correlate with the theta that you had for the rolling case. So for the theory, I think you covered the Lagrangian, at least in your in the theory that you, or rather with the assumptions that you had. You considered the rotation of both the ball and container, which was important for the problem, and you had the holonomic constraints, and also a sort of a tumbling condition of what happens when the ball hits, and then the capsule proceeds to tumble. What I think is very important for this problem and could have been missed in theory was, of course, friction, which wasn't considered neither between the ball and the capsule, nor between the capsule and the plane, which leads to sliding, because it's possible that, you know, you don't just have a rotation and a tumbling, but you can also have sliding. And this will, of course, affect the time that it takes to reach the source part. I think you could have considered different parameters, because that's something that I really don't understand, because you really just considered that the ball was actually fitting. So I think your radiuses for the hemispherical part of the capsule was the same as the ball. And I think that's a huge limitation on the theory, because it wasn't really mentioned in the problem that you have to just consider that. So that's the thing, that only the same ratio of the ball and the cylinder was considered, even though the sizes were different. I think you could have calculated a bit more stepwise velocity and the time, but I don't think that's that big a point if you consider the other thing that we're missing. For the experiment, I think it's very reproducible, of course, and you have a good setup using Tracker and your camera, and it gives meaningful results you can discuss, which we will discuss. And also you took into account errors, which is a very good thing in an experiment. I appreciate that. But I think you missed a variety of parameters. You missed inclinations, because it says in the problem for a certain inclination you need the time, but there was not much mention about inclination, just a theta, a phi. I think you were too fast with your slides.
Let's make a conclusion of your speech.
And so I come to the points of debate, which we can now move on to. May I begin the discussion?
Okay, sure thing.
Okay.
So
discussion, yeah, super.
Okay,
so I would just ask you, like, why did you just choose this one radius? And I want to make it even more, in a way, better, the results that you got. And I think one of the things that you could do that is to consider the fact that basically you just scaled your model. So you didn't have 5 different things. I think you just had one, and you have a different scaling because your ratio of the hemisphere and the ball, they are the same, right?
No, they are not. They change for every single ball, because the radius, as the ball gets bigger and bigger, its volume change with r cubed, while it's linear to r when it comes to the mass of the pill, as well as.
No, I think you misunderstood me.
Yeah, sure.
I mean that your ball is always fitting the hemisphere, right?
Yes.
Yeah. So
actually no. Like the theoretical approach consider, as you can see, 2 different r's, but the problem is experimentally. Like, it will still be a good thing for certain other radius. However, imagine that there would be some fluctuations there, some oscillations whenever it gets to that point, and that's very hard to predict. Like, I don't think there would be a model that we could take into account how it's going to bounce there and do that kind of thing. But it still works. It's still a good approximation. However, I didn't feel like putting it there because I already had, as you saw, short time and good results with some other experiments in order to put this there. So I think it was pointless.
I think it might have been a good idea to have that, but okay, as you said, you only considered that. I also think another thing.
I mean, I consider the different.
Where was the length of the length of the cylinder? It appears in the rotation, right?
Yes.
Okay, and then let's come down to friction, because I was really hoping we could talk about the friction and the sliding movement, because you have only considered that, okay, the ball hits, then there's a rotation, then the ball hits, then there's a rotation. Oh, you can have different things, right?
Yes, of course there is friction, and there is, of course, I consider friction, right? I think it's just a meaning of terms. I consider static friction. You're talking about sliding friction. So, because the static friction is the one that guarantees the holonomic constraints, because it's not.
Yeah, but if your ball is rolling, the more important part is the rolling friction, right?
No, the rolling friction is static, because the point of the ball that is in contact with the plane, or in this case with the capsule, is not moving with respect with the capsule unless you consider sliding friction.
Yeah, but you have to consider that.
Okay, so here's the point. If I write the equations, which I do have written here in my notebook actually, but I decided not to put it in there. But if you write it in terms of friction, I can also show you the simulation. I don't think we have time for that, but I do have the simulation ready for the friction forces, for the sliding friction forces. If you write it in terms of friction, there will always be friction, because whenever the ball hits there's no way the momentum is going to be the linear momentum is going to instantly be passed through to angular momentum. There will be a friction, and that friction will cause a torque in the pill that will cause the pill to rotate. And then we have certain conditions, like the rotation of the ball.
Yeah, I understand that, but what I mean is you're well, I wasn't sure if you had that slide because I couldn't see that, but
yeah,
the time it takes for this thing, especially because of the different inclinations, it will change because of friction. You can't just say that the ball will go, and that's what I'm saying. But what do you think, like, how would that change? And also, how would you consider sliding? So as I said, like, when the ball moves, it hits the capsule is rotating, but it's also sliding. Right? Because
that's what the friction model would say, the sliding friction model. So, but my point is, if I write in terms of that, then the only thing I will get is that the maximum velocity is achieved when I have a really high inclination and I just let it slide down. So it's not meaningful.
I don't really think so.
I'm
I'm sorry, I don't agree. I think
so if you see from my graph,
it would also be the case that if you use different radii and different masses and don't just fit the ball, that I think you will get different results, and I think you will have a.
If you have the friction like that, you have a acceleration. Even though it's a reduced acceleration, if there was no sliding friction, is just sliding down, it would still be accelerated, while mine reach a terminal velocity. So I'm telling you that it's gonna be faster, and then the equations will just tell me, well, just get the lowest friction force and the highest mass so that it's always sliding and then it's faster. And that's not meaningful, because I actually want to have an approach that deals with the tumbling part, the tumbling regime, and not the sliding regime, as I said in the beginning of the presentation.
I want to invite, guys, sorry, I want to interrupt you. I want to invite other people from the team.
If someone has a question.
To the discussion, right?
Please, you can raise your hand, or
while they're not talking, I could address other things you said. So I believe during the questions I was asked about the Lagrangian, and they asked me if I took that into consideration. I just use parallel axis theorem. It just allows me to change the axis to any point as far as it's parallel. So. And that solves the issue with the Lagrangian before that the other person asked me.
Would you like to comment? Yeah.
Yeah. Okay.
Can I ask one question to the opponent?
Yeah, sure.
You got, I think it was slide 17. You got your equation of motion for the rolling.
I will stop sharing. So if you want.
Yes.
Yeah, it's better to switch to the reporter slides.
Can you change
slide number 17? I'm working on it right now.
Yeah, you can keep
okay, there you go. What slide?
17, I think it was.
Oh, it's not passing. I don't know what is going on. Oh, there we go.
Yes. So this formula is only veiled where if the initial velocity of the ball is 0, right?
No, that's the acceleration. If you solve the ODE, you will have the initial conditions.
Yes, okay, but it's veiled for the all steps, or like only for the first one.
Yeah, I wrote it in that way because the initial velocity changes.
And did you have the answer for this equation?
I mean, it's easily integrable. It's just I can do it right now. It's y equals y0 plus y dot.
I think that will take too long to actually solve it right now.
But what I'm meaning, after each step, you will have another start velocity. Yes.
Yes. So you have another start velocity.
Did you do the calculation for the different steps? I mean, you can consider first step, then loses in your velocities, and another one, and so on. Or did you like set that the ball is stopped after each hitting process?
No, after each process, we conserve the velocity. Look at here. We find new velocity by conservation. And in the last step, we update the velocity and position again.
Could we look at your experimental results, please? Because I think we kind of missed that, and it would be nice for also everyone else to see what you actually get and how they correspond to the theory.
Sure thing. What results? These results? Or these results?
I mean, you tell me which one do you think?
Oh, each one?
Okay.
What was the question?
Let's look at the displacement with respect to time, okay?
Yeah, here it is.
Yeah, you have this, and you have one coordinate of being as function of time, there's displacement. Can you tell the difference between why you have 3 theories and 3 experiments?
Yeah, it's 3 theories because it's 3 theoretical graphs using the specifications of each beam. One, as you can see, it's beam 1, 2, and 3 are, in this case, A, B, and C. So
So it's just one theory, but it describes 3 different balls.
Yes, but yeah,
Okay.
it's 3 theoretical lines.
Why would you? If I see it like, especially in the left side, why do you think that as your time is going, your displacement seems to be moving away from the experiment moves away, and why do you think this is happening?
Not necessarily. Some of them, if you can see here, the experiments actually pass the thing. It's just random variations, I suppose. And of course, we are not considering friction, so there's a slight difference. We're not considering the slight in friction that makes it accelerate more or lose energy, and yeah.
And that was exactly what I wanted to say, because you see this in the beginning, the friction is starting to play a role, but you will only see, for instance, if you take the inclination and you take a really big slope and you start rolling it, I think your theory goes completely out of the bounds of what you get with the experiment. It's good for shorter lengths where you can compare, like it might take 10 tumbles, but if you had to consider 100, 1,000 of tumbles, I think this would not be good.
But I already explained you. I think that's a loophole. I already explained you that this theoretical formulation would say us nothing. It's just trying to put everything.
How will it say us nothing? I'm sorry, but it's
we've got points of both participants
does anyone
this
else
question. Okay, do we have any questions from the teams? We actually have now teams discussion.
Oh, maybe if I say something.
Yeah, go ahead.
May I ask any question?
Yes.
Yeah.
So what I wanted to say, can you go back to the slide where you was recently? I wanted to ask actually, why would you expect, like you have on the graph on the right, why would you expect that the line at the top, it goes just like out of the theory, while the middle one goes completely like according to the theory? And yeah, like what was the difference?
It's just random variations. I mean, there are effects like that. For example, this one on the left is it's actually just the same as the other one, but this one is also the same beam as the other, the up one, the one above, and it goes above after a few times. So it's just random displacement of measurement as any kind of uncertainty, statistical uncertainty thing would cause, just by repeating experiments many times.
Mm-hmm. And it's the same like for every experiment you conducted, that it's always there is like this statistical error that occurs every time, every single experiment, right?
I'm sorry, what?
I mean, like every experiment you conducted, when you plotted theoretical part against the experimental, was there every time a like a difference between those two, like this statistical error that you're talking about?
They were sometimes up, sometimes down, and sometimes they match, like the orange or the blue, the blue one here. So it's just, I mean, I do not have a completely controlled environment, so.
Thank you both. I would like to ask to the reporter two things. First, if you had an infinite inclined plane and you let your pill tumble down, but you had very good, very rough material, so let's say it wouldn't slide as long as we observe, but would the velocity increase indefinitely?
So are we saying? Oh, I'm sorry, I'm almost running out of air. There we go. So if we had this, in this case, so are we considering that it's fully attached to the surface?
Yes, my question boils down to, does your pill reach terminal velocity or not?
It does reach a terminal velocity, yes.
Why?
Well, first of all, we can see that if there are no other forces acting on the whole system, we can just say that there is the gravitational force. So it's definitely limited by free fall. Another thing is we just consider the pill ball as a system, and then the forces acting on it are just the gravitational force. So In
Okay,
any
okay.
case, it's just
And sorry to interrupt you. Just one question. In your experimental results, could you go to the slide where you show the experimental results again?
I can.
Sorry if that takes a bit too long, but I wanted to check
There we
something.
go.
Okay, so in your slide on the left, the displacement, which is clearer, I can more or less see the kinks in your theory that would show each rolling down, right?
Yes, each loss of momentum and energy because of the ending of the tumbling. Yes.
Okay, but it doesn't seem to me to match the experimental data. Could you show me in the experimental data when a tumbling phase ends? Yeah, there is better, maybe.
Yeah, so you see, it does match a little bit. Of course, it's not a perfect match, but if you see, even for larger times, you still have the this change in momentum down there, and here in the beginning is very easy to see. So it goes and then it does like this. So it does have the same shape. Sometimes not, it does not match exactly. And one thing I could say is that if I plot it here with it just sliding down, will have a completely different, or sliding or rolling down, I will have a completely different thing. So the theory doesn't only match these little variations, but it matched the overall behavior. So if I plot some other kind of prediction there, if it's only rolling without losing energy or anything, it would just deviate completely from the experimental thing. So also the general trend is also predicted by the theory, not only these things.
You're very detailed, thank you. Can we move to another member of jury, like Bogdan? Can you ask your question?
I have very silly question. In discussion, we came to points that, okay, we can include to your model sliding friction. And you said that in this case, lowest friction, in fact, zero friction, and highest mass will be fastest moving down, yeah?
Yes.
Do you still stand on this point that mass is important?
Wait, I'm sorry, what was the question?
So you said that lowest friction and highest mass. So in these limiting cases, do you still say that mass is important?
Mass is not important if it's just sliding. If it's just sliding, it's just going to slide down with that velocity. But mass is important for sliding in another perspective. If it's near zero but not zero, then it would be super easy for the pill just to breach and slide through. So that in that case, mass is important.
So, and other question, have you investigated how does difference between size of your small ball and this tube, how difference between their sizes matter?
Between the ball and what?
And this tube pill that you put your ball in.
Oh, yeah. So I always use, as it said in the video, not so tight fit between the radius and the other radius. But my theory also, as you've seen, I have two different radius, so it also englobes that. However, the problem is whenever you have a small thing, it's gonna oscillate in there with a quite unpredictable way. So we wouldn't have good results. So I could try to make that, but it would be kind of useless, and I wouldn't actually be able to answer the problem of what is the fastest beam, what is the fastest velocity, and that kind of thing if I just consider that.
Okay, but you said that this effect is present, yeah?
Yes.
Okay.
Okay, Roman, your time for question.
Yeah, I have a short question on the displacement you are plotting. Is the center of mass of the whole system?
Is the center of mass of the ball? Yes, the center of the mass.
So I'm very surprised because during the tumbling phase, it should not move. So it
does move because there is a very small, small radius that makes it move anyways. Because it's rotating, and then there is static friction, so the point over there doesn't move, so the whole thing has to move in order for the thing to continue. So if you imagine that there is a ball here and it's rolling with respect to these, so it does move a little bit while it's tumbling.
your slope remains the same. So
yeah, but I would expect to see the different phases on this graph. And I'm a bit surprised not to see them.
Oh, these are the different phases. Look at this.
Yeah,
here
maybe on this specific plot we see something, but on the other one we don't, and that was a bit
oh yeah,
surprising.
these ones. Oh, okay. I see what the problem is. It's because here it's too far away because there are too many iterations that you can see. But in all of them, if I was able to zoom it in, you would see that there is these two different phases.
Okay.
So one
Okay.
with a smaller acceleration
Thank
because
you.
there is the.
Thank you.
Yes, thank you. Nina, do you have any question?
Yes, I have one
Okay.
question.
Go. Yes, far away.
I think I can't see you such regime as the trembling effect. And I can ask you a question. What do you think about the relevant parameters that influence on appearance of trembling regime?
Oh yes, I had a slide for that. We passed through extremely quickly because I was short in time, but we can see it. Oh, it's actually the other way. We can see it here. These are the conditions for tumbling. So I pretty much just say that the torque is greater than 0, meaning that the ball is gonna be able to force the whole peel to rotate. And the other boundary case would be if it's sliding. It is sliding in every case, but then we need to tell ourselves, we need to answer ourselves how much sliding are we willing to get. You understand? So if I say, oh, I want this much, and then so that I lose very few momentum, then I can plug it in and then calculate another requirement.
Thank you.